Yeah. Hello, good afternoon, everyone. This is the last live session that we have uh, in this course. Okay, so I hope you have been enjoying the course. So since I do not see any specific questions, I will actually try to discuss some of the things that are of interest related to this course. Okay, so I hope you can see the screen, and basically we have been talking about some of the interesting aspects in nuclear physics and particle physics. Basically, at the nucleus is at the length scales of about a Fermi, and the subatomic particles are a few orders of magnitude even smaller than that. So initially we had a good discussion on the nuclear models, nuclear properties, and then we went on to actually talk about the elementary particles as we know them now. And we said that apart from the electrons and the quarks that make all of neutrons and protons and neutrons, yeah. Okay, so that we have other particles similar to electron, muon, which also carry a negative charge, electric charge, and the tau electron, which carry again a negative one electric charge in units of electronic charge, same as the charge of the electron. And there are these neutrinos, which are chargeless, electrically neutral, and mass is almost zero. And then we have different types of quarks. To look at the proton and neutron, we need only what's called the U type and the D type quarks. But we also have other quarks like C quark, S quark, T quark, B quark for consistency of the mathematical model to start with, and then later on we found that there are particles which we can identify as made of these quarks. Like there are strange, this quark S is called strange quark, and there are mesons and baryons like proton and pi meson, which are made of these strange quarks. Similarly, there are these charm quark, which is denoted here by C, and bottom quark. There are particles, bound states of these particles, these quarks are seen. Top quark, on the other hand, is one single particle which is very heavy and therefore do not form any baryon or meson like other quarks. So top quark stands apart in this sense among the quarks. But we have discovered top quark also, and we know the properties of this very well now. And all other particles similarly are discovered and then identified and then studied experimentally. Theoretically, we understand all these things and then all dynamics of all these particles somewhat well. And the last of these elementary particles was the Higgs boson, which was discovered in 2012, which has a spin of 0. This is the only particle which has spin 0, which does not have any spin quantum number, so to say, and electrically neutral, but it has some mass. It's heavier than the proton, something like 130 times that of the proton, in fact, and it's but lighter than the top quark. So of all the elementary particles, top quark is the heaviest one, and um, yeah, other particles are all lighter than that. And there are this photon. Of course, we are familiar with photon, which we have been uh, studying through classical electrodynamics to start with, its properties, basically all the electromagnetic radiation, light and X-rays and all other radiation, basically at the quantum level, the streams of these photons. But we have been studying those as electromagnetic waves in the classical theories, and in the quantum picture, we have understood that that's not sufficient, but we have to actually invoke these indivisible energy packets that are associated with this. And similar to the photon, which is associated with the electromagnetic interaction, we have the weak nuclear interactions and the corresponding gauge bosons, which are called W2 charged, electrically charged W bosons, and a Z boson, which is electrically neutral, and gluons, which correspond to the strong nuclear interactions. All these things we have kind of studied and then discussed in your course somewhat. And we have perhaps mentioned otherwise in the if not in the lectures, in the last discussion that we had in the live session, maybe, that all these particles, excepting the first few, these U, D, and electron, okay, these three, all other particles are somewhat exotic in the sense that everything around us is made of all these three particles, and then none of the matter that is there with us actually we see any of these particles. Like, for example, we don't see anything made of top quarks or B quarks. They are very, I mean, the structures that are made of these, like the particles or bound states of these, like equivalent to the proton, we can think about the baryons made of heavier quarks, other quarks, but they are all very unstable. Similarly, W boson and Z boson, they are all unstable particles. Top quark also is very unstable. We produce it and then it decays in no time. Higgs boson is also unstable and decays in no time. So in the elementary particle physics, we have been actually studying them for consistency of the theory and then understanding all these things. And then, of course, there are, although unstable, we can actually discover their decay products, etc., in the detectors or colliders and detectors or in the cosmic rays. For example, in the Large Hadron Collider, we produce all these particles, and that's how we detect this Higgs boson. Similarly, cosmic interactions have allowed us to actually understand all these many other particles which are there. So although we don't see them in usual matter around us, we have laboratory experiments where we have been actually studying them, and then we are confident about their properties and their existence and their properties. But now there is one place in the whole universe, one place meaning one scenario that you may consider as in the universe that we cannot actually live without really considering their dynamics and understanding their properties. That's when we actually look at the origin of the universe. So when we actually think about how the universe is actually as such originated and then evolved, we have various different models. In fact, we had many different models. Presently, we are actually being zeroing in onto some particular specific scenarios out of all these various different models. So the presently acceptable scenario, by acceptable I mean which are consistent with all experimental facts, astronomical, astrophysical, and terrestrial experiments, and considering the mathematical consistency otherwise, leads us to a picture where the universe actually had some kind of infancy. Beginning is a point which physics is not yet prepared to address. However, the infancy of that, in the sense that very early times of its evolution, we can think about it as a highly dense and then very highly energetic, with large energy density and then high temperature kind of a situation where all different particles at the elementary stage can be thought of as existing. In this situation, the energy, we can think about energy in the sense that there are a lot of radiation, say for example, and the temperature as the radiation energy of the photon, the temperature in the sense of a photon. Temperature is basically the energy of interactions, and then with the photon as a collection of photons that we have in the has a large amount of energy, then we say that the temperature corresponding to that is very large. Now, if the photons having large energy exists, then we cannot, for example, form atoms. If there are atoms there and also high energy photons, then these high energy photons will interact or scatter or with the atoms or interact with the atoms, give energy to the electrons and make it fly away from the atom. So bound states like atoms or even nucleus, or in fact even the protons and neutrons could not have been existing at very high temperatures. So at that stage, we can only think about elementary particles like elementary quarks and gluons and W bosons, photons, etc., coexisting in them. And then, universe, according to the general theory of relativity, it evolved. It evolved, and it evolved. When as it evolved, it expanded and it cooled down. When it expands, anything like any hot gas, if it expands, then it cools down. The average energy of the particles inside that, including the photons, become very small. I mean, smaller compared to the earlier stage. So as it evolved and then as it cooled down, the temperatures were not that large then, so that some of these bound states exist. First, it could form these baryons and then protons, neutrons, and other baryons. Protons and neutrons are stable and therefore they stay there. And then the temperature as it cools down, as the universe expands further, and then the protons and neutrons have small enough kinetic energy so that they can actually come together and then form nuclei. So this is the period of what's called the nucleosynthesis period in the cosmic evolution. And further on, as we go on, reducing this temperature, expanding the universe, and then reducing the temperature. The universe expands on its own, and the cooling it down. And after a long time, then the temperature is of the order of the atomic spectra, the energy level of the atoms, and at that stage, then the electron can combine with proton to form hydrogen atom, and this kind of thing goes on, and therefore these neutral atoms are formed. There were also deuteron and helium and traces of lithium, etc. that could be in the nuclei were there. So those atoms could also have been formed. So creation of matter and formation of the nuclei and further the larger structures like atoms, etc. And as we go on, the universe cools down, and then these atoms and things like that will come together to form bigger things, and then helium, for example, large amount of hydrogen atoms, and then you can think about some gravitational perturbation, and then which actually make all this cloud of this helium actually combine together, condense together, and you form structures like galaxies, stars in that, and various different structures of different masses, different size, and various different properties. And that's where we are now. So as this goes on, and then whatever presently that we have are formed like that. So elementary particles, then protons, neutrons, etc., and then the nuclei, then atoms, and larger structures. That's how we imagine this has to happen. So this different epochs we can actually think about in this. I have actually listed it here, some of these things here. And one important and interesting period is when the atoms are formed. Until then, the electrons and protons, etc., or the nuclei, were electrically charged, and then they were actually in a kind of a soup. This is the plasma, electromagnetic plasma that we have, and photons are highly interacting with this plasma. But after the cooling down of this universe further and combining the electron with protons, forming atoms, hydrogen atoms, and then helium nuclei with electron to form helium atoms, these photons interaction with this atom is very feeble, very weak, because atoms as a whole are neutral. So there could be some remnant interactions, but there is no real clear interaction of this, like in the plasma case. Which means that the photons from them are kind of freely propagating. And these are what's called the free streaming photons, which are called the cosmic microwave background radiation. Microwave, because when we look at them now, the energies are in the microwave range, or the wavelength is in the microwave range, and energy corresponding energy. So this you can imagine as a kind of important aspect here. And as I said, many different structures were formed with all these things. So presently, there is something called, apart from all these particles that we know exist terrestrially, when we look at the astronomical and astrophysical data, observations of astrophysical and astronomical observations, tell us that when combined with the general theory of relativity, tells us that it's not possible. I mean, there are other particles or other kind of matter that exists, apart from the particles that we have been talking about in this course, or the standard particles. Apart from the standard particles, there are additional particles which exist. Important thing is that these particles are the property that they do not interact with the electromagnetic radiation, which means they are not electrically charged and they do not really have electromagnetic interaction. Not only that, they don't have any strong interactions or anything. They could be they have some kind of a very weak interactions like the neutrinos, and they have to have some mass. It is not sufficient to have light particles like neutrinos. It has to be sufficiently heavy. This is the usual picture, but there are also alternative versions of this where one could actually have very light such particles, and then there could be a different kind of dynamics, and which are consistent with all other experimental observations. We will not go into that. But in a particle physics kind of a picture, they have to be sufficiently heavy, sufficiently large mass they should have to actually accommodate all the experimental observations that we have. They are called dark matter because they do not interact with photons or electromagnetic radiation, electromagnetically neutral. And therefore, we cannot actually see. All our astronomical observations are through photons or electromagnetic radiations of different. It could be the visible spectrum, like we see sun, stars, and moon and other planets. And we could also do look at other radiations like X-ray radiation. So there are X-ray astronomy, gamma ray astronomy, radio astronomy. All those observations actually look at specific wavelengths or frequencies of electromagnetic radiations. So far, we have been relying pretty much on this thing. Very recently, we have been also able to look at gravitational waves as a window to understand, as a device or as a tool to understand the stellar dynamics. But that's very, very recent, and we have very limited observations so far. And also, it is quite difficult to pick up. And so, because of all these reasons, we call this the dark matter, because they are not visible to us in the sense that no electromagnetic radiation is going to come from them to actually indicate their presence. So in the standard model, we don't have any possibility of explaining that with the particles that we have been talking about so far. There are also other kind of problems, in a sense, that the standard model faces, because all matter that we have seen, everything that we see in the universe are made of matter particles like electron, proton, etc. But on the way we had talked about the antimatter, like positron is the antimatter corresponding to electron, and antiproton is there. So we don't really have structures made of it. So this has to be explained, and this particular observation that such an asymmetry between matter and antimatter is seen in the universe at a very, very large asymmetry. It is because it's known as the baryon asymmetry, and that's another thing that the standard model has to explain. We will actually look at the dark matter case today, very, very briefly. So we'll go back to this cosmic microwave background radiation. As I said, when electrons combine with protons to form hydrogen atoms, then this happened in the evolution of the universe at around 380,000 years into the evolution of the universe. And then universe became, we can talk about it as became transparent, in the sense that what is transparent thing? The transparent things actually allow photons to go through. You take a glass and then place it in the way of light, light will pass through that. You take a wooden board and then place it in the way of light, that will not pass light through that. So they are opaque. So which means that photons are absorbed by the wood or a metal or whatever you take. Whereas the glass does not bother about, or the photons do not bother about the glass. It can just freely pass through that. There's some bit of an interaction, and then because of that, there's a bit of refraction and things like that. but by and large, they can pass through that. So in the case of neutral atoms, the photons are more or less like that. They just pass through that. This one. So if you have hydrogen gas and then send photons through that, it will just pass through that. And this is what we call the cosmic, because it originates not from any sun or any particular star or a galaxy, but it has its origin in this fashion, like from the primordial beginning of the universe itself, it has been there, and they have been moving freely. And when we see it now, because the universe is expanding, etc., its energy is getting reduced, and then the whatever the wavelength corresponding to that now presently is the microwave range. Therefore, we call it cosmic microwave background radiation. And it is supposed to be an isotropic, and from all directions it is coming with the same thing, and there is no difference when you look at different places or different directions. It's homogeneous and isotropic. It is all discovered some time back. In fact, there are stories with that it was discovered accidentally. But while another group of scientists were actually looking for it, they couldn't find it. But these two gentlemen could find it without looking for it, because they were studying something else, and but they found this. And then further on, this was acknowledged and understood that it's basically the cosmic microwave background radiation. There are ways to establish all those things. And in fact, it is also the energy spectrum intensity was also mapped, and then it was understood that this looks like a background black body radiation corresponding to a temperature 2.78. Now it is more precise, and I think it is 2.75 Kelvin or something like that. So, and it was independently discovered by different groups. And presently, there are cosmic space telescopes, like there's this thing called cosmic microwave, okay, COBE. Yeah, there were different space missions, microwave background spectrum from COBE. COBE is one of the early space missions, and later on there was this WMAP, and latest was this Planck mission. So these satellites go outside the periphery of Earth's atmosphere, go into the space, and then stay there, and then take data of photons. So this was specifically tuned to actually take the data of the photons from all different directions of the sky. It stays there and then takes all these things for many years, collects all the data, and then now we have analyzed that. 2013, by that time, the data taking of the Planck mission was over, and then now we have kind of a very good picture of this. So there are ways to actually analyze it. We won't go into that, but bottom line is that first of all, there are light coming from known galaxies and galactic groups and stars and things like that, and we know those from other observations, and we can subtract that. And after subtracting all the known sources that way, specific sources, we have this background light. That's what we have here. So the background radiation is basically after subtracting all other light or other radiations that we have from galaxies and other these things, subtracted from that. It is expected to be isotropic in the sense that it doesn't matter. So this particular picture that you see now is essentially all of the sky put in a kind of a picture like this thing, so you can actually imagine this as the whole sky. Okay. Now this is supposed to be uniform, and it is supposed to be isotropic in the sense that it doesn't matter where you are looking at, it is all the same, and that should be so. But you can see blue, red, and then other slightly different colored patches here. What are those? In practically speaking, we see that there is a small difference between two different regions. It's not completely isotropic and homogeneous. It's not the same. There is some fluctuation when you take two different points. This is not experimental uncertainty, experimental error. We know the experimental errors, and then taking into account the experimental errors and things like that, there are differences beyond all those things. They stay there even after considering the experimental errors. So this is beyond what the experimental error tells us. And these differences can be actually understood in terms of the differences in the temperature or energy or electric field or magnetic field and things like that. So this is, let us say, temperature difference. So we can actually think about the two different regions, one with the blue and another one nearby with the red, having a difference in the temperature, with red being slightly higher in temperature compared to the blue. The difference in these temperatures is very, very small. For example, if delta T is the temperature and then T is the difference in the temperature and T is the average temperature, delta T by T is of the order of 10 power minus 5. So that is very small, but we do have this. So this is an important thing actually. So people have actually tried to understand these fluctuations in this temperature or these differences in the temperature between different neighboring points, different regions of the sky. One way is to understand that is to actually think about it as these photons, as we said, before free streaming, were interacting with the plasma inside in the universe at that time. We did not have atoms, but we had neutral electrically charged electrons and nuclei and protons. So photons were interacting there. So any small deviations in the in densities or properties in different regions would perhaps will actually reflect in the light or the photons coming from these different regions. Photons, after interacting with these two different regions, go through, and then they, after some time, they are free to move around, and they will have this, they will record, they will have the signature of these differences between different regions. It could be a density perturbation, it could be something, whatever that causes this, but the differences in that could actually reflect in this. So we believe, therefore, that it's that changes in this or differences in this in the plasma that's causing this. So at that time, the plasma can be actually thought about as a kind of a fluid dynamical model. You can think about this as a continuous medium and study how photons interact with that and what are the other dynamics that we have. So we have electromagnetic interactions, and there is also gravitation, because the general theory of relativity, there can be curvature differences at different points. The gravitational interaction can actually bring in differences in this thing because of the density perturbations in that. So these things are dictated by the total amount of matter in the universe and the matter which interact with the photons, which are called baryons. So we consider those particles which interact with the photons as protons and particles like protons, which are called baryons, and electrons and particles like electrons. When we consider the mass or the amount of matter or the mass or energy corresponding to electron and that of the proton, the mass of the electron is negligible. Therefore, usually it is called baryon density or baryon content of the universe. So this baryon content of the universe is one thing which we can read out from analyzing this difference in the cosmic microwave background radiation. There are specific ways to do that. Again, we will not go into the technical details here. This slide is just to tell you, for those who are not familiar with this kind of analysis. Like if you have heard about Fourier analysis. This is similar to Fourier analysis, but we are not dealing with trigonometric functions like sine or cosine theta, but we are talking about some other functions which are denoted here by y, l, m, theta, phi, and they have their own specific name. For those who have heard about it, it is spherical harmonics. And these spherical harmonics are actually the ones that are similar to this, having certain properties as functions like that of trigonometric functions like sine and cosines. And so these temperature fluctuations can be actually expanded in terms of this, like Fourier expansion of any function. So this can be thought about as some function, temperature fluctuation over the different places or different regions. And we can consider them as some in terms of some Fourier expansion or the equivalent of the Fourier expansion in terms of the spherical harmonics. So, and all the other things that we are reading out are looking at this analysis. If you don't understand that, that's okay. You can just take the result that people have analyzed this thing, tell us. The bottom line is that total matter in the universe, if is consider it as 1, then 68% of that is what's called dark energy. Okay, they do not have the usual gravitational interaction, and the total matter content is about 32 percentage, which are gravitating matter. And out of this gravitating usual matter, with like 5% is what make the baryon content or the usual matter, making all the stars, galaxies, and everything that we have been observing. Okay, and the rest of it, which is 27%, is what we described earlier as the dark matter. Okay, so here all these things can be read out from this CMBR spectrum analysis. This is called a power spectrum analysis of the cosmic microwave background radiation. So this is one way to establish that there is this dark matter quantitatively. But qualitatively, dark matter, indications of dark matter has been there for with us for a long, long time. Starting from the 1930s, we knew that there's something which is not complete when we look at the stars, the galaxies, the light coming from the galaxies. The way the light coming from the galaxies, we can actually look at the amount, find out the amount of light coming from that, and therefore the mass corresponding to that mass of the galaxy. We can also find out the individual stars and their motion, which means velocity of the stars in the galaxy. This had been done painstakingly by observers, and we have two different, one curve for the light, the velocity of the stars, that if you plot them against the distance from the center. So the observation says that it actually goes on kind of a sharp increase initially and then flattens out, but it doesn't come down. It just goes on like that. Whereas what is expected from kind of the mass distribution that we usually expect, like almost all the mass is concentrated in the center because of the gravitational thing, and as we go away from the center, the mass will actually come down and gradually become zero. So that is what we expect. If that is the case, then we expect the light, because of the Newtonian dynamics, we can actually tell that the velocity of the stars in the periphery should actually come down. Okay, it should go like v square should go like 1 over r, whereas observations say otherwise. So this is one of the ways to take care of that is to actually think about some kind of a additional mass that we have there. So if the dark matter is present and spread through the galaxy, then this can be explained. I will not go into the calculation, etc. here, but so it's possible to explain if we consider dark matter to be present in the galaxy. There are also other observations like gravitational lensing. So if you're actually looking at some distant galaxy, usually we will see it as kind of a small dot. But if there is some mass or galaxy in between, then we will actually see it as a halo. That's okay. That's no problem. This can be there if you have a galaxy in between. But the point is that we can estimate the mass of this galaxy in between, the mass of the galaxy in between, which actually makes this lensing possible. And the radius of this this halo will depend on that mass. And again, it is the observationally the radius is found to be actually different from what we expect in the usual case of having only the mass estimated from the light radiation coming from the galaxy. So this is also indicating that there is more than just what we can estimate through our observations from the radiations of electromagnetic spectrum. So there are also other things which I don't want to go into the details. I strongly urge you to actually, whoever is interested in it, go through the literature otherwise. Now we also have books on this, but you can certainly get a lot of information from authentic sites in the internet. But it is established that there is something called dark matter, which we have to kind of understand. So what are the properties of this? So from particle physics point of view, we want to understand this as in terms of some elementary particles. There are other explanations, or at least people have been trying to explain other ways. Many of those actually contradict with, see, this is not one single observation. There are completely independent scenarios which actually require this to be explained, like the cosmic microwave background radiation, the lensing effect, the rotation curve of the galaxies, and other reasons. These are completely different scenarios. So there are explanations for one which may not be agree with the another one. There may be explanations which are agreeable, which agrees with a few, but may not agree with the other one, etc. By and large, the situation at the moment is that particle physics candidate, if something is there, that could kind of explain all of these ones. There are also some other explanations which are compatible with all the explanations, all the observations. Still, not necessarily it is a particle physics, a new particle that we require. But this is an easy and straightforward way to understand. And that is the way we understand all the other matter. Therefore, it is natural to actually expect that there are this some elementary particle which constitutes this dark matter as such. Firstly, they don't have electromagnetic interaction. There had to be some massive particle, because otherwise all those rotational curve and things like that cannot be explained. And lensing effect, it will be difficult to explain such observation. It has to be very weakly interacting particle. It cannot be strongly interacting and the same, because otherwise we would somehow see the signature of that. Okay, neutrinos are there with us, which is weakly interacting, electrically neutral. It has some small mass, but the point is that they are too light for many things, including gravitational lensing, to be effective. So we will not consider that. So in what's called the weakly interacting massive particle scenario, people have been actually studying this very, very intensely for decades now. And many different aspects of that is being considered. So we keep asking questions. One of the things that it has to be compatible with the astrophysical and cosmological um, observations and the theoretical model therein. And secondly, if we can actually think about terrestrial experiments, like if they are elementary particles, they should be produced in the Large Hadron Collider, for example, or any particles laboratory experiments like that. Okay, and we should be maybe able to go and then check for those, the presence of there, like we have been trying to understand or discover Higgs boson. We can think about devices or methods to actually discover dark matter in such collisions. Then the other thing is that when we are talking about galaxies and galaxies being having all this dark matter presence in the galaxies, we are also part of the galaxy, and our Milky Way also has this dark matter naturally. Then this dark matter, if we are actually passing through that dark matter kind of a distribution of the dark matter, Earth will also be, as a solar system, and Earth will be passing through that. If that is so, then is it possible that they, in their interaction with some nuclei or matter on Earth, can be detected? These are called direct detection experiments for dark matter with some nucleus or some standard particles can actually have some kind of interaction between each other, and then we may be able to find that. Then it is possible that there are regions where these particles are highly dense, gravitating and highly dense, and there they can actually annihilate each other or interact with dark matter. Dark matter interaction can actually give you the elementary particles, or particles which we can detect. These are called the indirect detection methods. So we don't really directly detect this thing, but some elementary particles like proton, electron, positron, or photons, etc., coming out of dark matter interactions, annihilations of the dark matter. These are the possibilities that we have, and then one of them is the direct detection. We have been actually trying to do. There are experiments which are specifically designed to look for dark matter as we are passing through. So direct detection experiments have been going on. Essentially, the idea is you try to take some large amount of some clean non-nucleus, and then in that case, basically, you can calculate if there is some kind of dark matter interacting with this nucleus. Essentially, what you think about is that not any, some kind of an energy exchange between dark matter and nucleus. This recoil that will result in the recoil of the nucleus, and this recoil, since that nucleus is in this big, large detector volume, it will interact with the medium there. The particles that other particles there, and then it will actually bring out its excitation energy in terms of the photons. And these photons can be detected, keeping some kind of photon detecting devices like a photon multiplier tube or some cameras or things like that. So essentially, that is how you actually find this one. And that experiment goes on. It are very sensitive experiments, and I'm sure you don't want to. This slide is not to go through each step and then explain it. This is just to tell you that number of experiments that actually are part of this kind of direct detection thing. Each of these names actually correspond to different experiments. And there are these bounds on the mass of the particle and then the nuclear cross-section. As I said, there is this interaction that happens. The probability for certain interactions, and that can depend on the mass. So what we can say is, if the mass is so much, and if we have this probability larger than certain amount, we would have seen it. And if we are not seen it yet, therefore its probability for that thing to happen should be smaller than this. So that's how you see it. Anyway, so basically we have not seen anything, but that puts a kind of a limit on its properties. Like the cross section, what we call the interaction strength, should be kind of smaller than certain amount that which can be precisely calculated from the experiment. Okay, so and again LSC experiments are also there, which has been going on, and then we have not seen anything yet. Basically, dark matter is not detectable. Otherwise, um, yeah. So because they are dark, they don't. So what we can detect is some things which can actually interact with matter. Detectors are usually some matter, some material which will interact with this particle which is coming in and absorbs energy, etc. And dark matter, being dark matter, will not leave any signatures and any energy or anything in the detector. So therefore, that is how it goes. They will be just missing. But good thing is that there will be associated particles at the same time produced along with it. So momentum and energy conservation could be actually used to see that there is something missing. This is pretty much similar to the discovery of the fact that the beta decay, we have something missing, and that missing thing is some particle, elementary particle, which we call the neutrino. And this is pretty much similar to that we can actually see, infer that there is something when by looking at missing particle identification. So that's how it is. I think we we have to stop now. Basically, that studies of dark matter is a very, very active area of. Okay, sorry for the typo. Recent particle physics research in particle area of research in the particle physics is thing today. Okay, so a lot of research is going on, and it's one of the areas that people are actively participating in today. We don't really have any kind of solid proposals for this one, but there are many models are proposed, many ways are being proposed, but experimental validation of all this has to be done. And there are also other activities in the fundamental particle dynamics that we need to understand. Baryon asymmetry is one of the things that we said, and many other interesting aspects are there. I hope the course has actually given you some kind of a basic ideas about particle dynamics, and have kind of kindled the interest in you to actually learn about it more. And I hope some of you will actually take that up and then study further in this direction. And I wish you all the best for that.